All right, everyone. Okay, so today we have education systems All right, everyone. Okay, so today we have education systems All right, everyone. Okay, so today we have education systems about making sense of these orders.
Thanks very much, Arno. So let me start by emphasizing what a privilege it is to address you today, what a pleasure it has been to talk to some of you today, get to know you, this department. It's really been a great visit so far, so thank you very much for that. So as Arno said, I'll be talking about disordered systems, but before I do that, I just want to mention, I was really fond of this Alberta and Albert mascots you've got here. They're the only mascots I know of who have solved a two-body problem. So they must be truly exceptional, and I hope to see them in action at some point. All right, so when we're talking about disordered systems, kind of given this subtitle, and it's not so much about these three characters, but rather the fields that they've come to symbolize for us, namely geometry, motion, and magnetism. And so I'm going to break the talk into three parts. But before I do that, let me just say what in general a disordered system is. So a disordered system doesn't really have a precise definition. It's more of a catch-all term, but here's something we can work with. So let's say that a physical system is, quote, disordered if the microscopic quantities that govern its behavior are random variables. And I mean random variables in the sense of, functions from some abstract probability space to, say, the real numbers. Now this, right, doesn't really mean much. We'll get to some examples, but let me mention that in general, it describes complex systems that have many interacting parts, often that are behaving out of equilibrium. So disordered systems, the paradox of it is that the insertion of random variables actually makes things easier rather than harder, because the random variables capture all of the difficult stuff, the interacting parts, the complicated system, and then we can use tools from probability theory and analysis to understand what happens when these systems get very, very large. And I've already revealed to you that somehow scale is going to be important. So at the microscopic level, we're just going to have these random variables. Often they'll just be independent things, and they're going to interact in some novel way. But then when I make the system very large, we're actually going to observe something that is deterministic. So some limiting behavior will emerge out of the disorder at the micro scale. Okay. All right, so as I said, we're going to talk about three different parts. So I'm going to give you three examples. And the reason I'm going to tell you three stories instead of just one is because there is a through line. So I want to describe some of the common themes that emerge from the study of disordered systems, namely geometry, motion, and magnetism. And that theme, at least for today, will be variational formulas. So in each one of these cases, as I make the system very large, we're going to get a formula for some law of large numbers. So every time you see kappa, that's just going to be the outcome of the model's law of large numbers. So when things get big, there's some statistic we can study that has some law of large numbers behavior. And the variational formula is somehow a creative way of writing that law of large numbers outcome in terms of some optimization over some abstract set. Normally that set will be a set of measures. So whenever you see mu, it's going to be some kind of measure, so some infinite dimensional object. And the mu that ends up making the variational formula work is called the functional order parameter. So what these functional order parameters do is it tells you what is the physically relevant thing to pay attention to in the system, as captured by this law of large numbers. And once we have the law of large numbers, this variational formula, we can do interesting analysis to it to recover some of the physical properties that you observe on macroscopic scales. Okay. All right, so throughout the talk, I want you to interrupt me as much as possible, ask questions. Any comments so far, anything that you're curious about? I know I haven't made any precise definitions, but anything anybody's wondering? Okay, so let's get to chapter 1. So here is Euclid, whose view of the natural world, right, through his book, famous book, Elements, has now given us a view of the natural world that we take for granted. So just to emphasize how much that's the case, let's suppose that I put 2 dots on this page. and I ask you, what's the fastest way to get from dot 1 to dot 2? Well, I think intuitively, right, it's just the straight line path, right? That's instinctively what we go for. But actually, what if I told you that's the best path? Well, in what world is that the best path? That's the fastest way to get from point A to B. Well, that's our world. So in fact, if I gave you a map and some 2 points on the map, and I said, what's the best way to drive from point A to point B? If it were a straight line, you'd get suspicious. You'd say, well, that's just as the crow flies, right? What are we doing? Driving through forests? So in fact, disordered geometry, although we don't think of this landscape as some outcome of random variables on some macroscopic scale, the study of disordered geometry can give us insights into landscapes that look like this and the universal phenomena that we see when we look at, say, maps of how to get from point A to point B. So now I'm going to describe for you a model that captures some of this behavior. It's called first passage percolation. It's just one of a number of random growth models. And it goes back to Hammersley and Welsh in '65. And here's what we define it to be. So I'm going to start with the integer lattice ZD with its natural edge set. So you can move any individual coordinate plus or minus 1. That gives you the edges of the integer lattice. So here I've just drawn a subset of the integer lattice when d equals 2. And then here comes the random variables. So this is the disorder part. And whenever you see a blue X, that's always disorder in this talk. So pay attention for the blue X's. That's always this insertion of random variables into the model. Okay. So what are the random variables in this case? Well, they're going to be assigned to each edge. So each little edge here. So we have, here 2 vertices and the edge connecting between them. And each edge is going to be associated with an IID random variable, which we call XE. And I'm just going to assume they're always non-negative. And that's to have the interpretation that it's the amount of time it takes to pass that particular edge. So for instance, this edge I was highlighting, right, this red skinny edge, that's quite a large edge. That's why I colored it red. And if you look at a thicker green line, that's some edge that's relatively small. So here I actually sampled, right, independent and identically distributed random variables that happen to be uniform on the unit interval. Now, it's just some choice, but that's the outcome. So once I've laid down this random environment, then we can define for any given path. So here, for instance, I could take the straight line path that we think from with Euclid from 0 to say 20 units in the horizontal direction. I could say, well, what's the passage time of that path? Well, it's just the sum of however many edges it goes across, and I just add up the weight of each edge. So that's just the definition of a passage time for a path. Now, this may not be the best path. It's certainly the shortest in Euclid's sense, but it's no longer the shortest in our sense. So namely, I could notice how at the end, I cover some of these large weight edges. So I could make a modification and actually the passage time goes down. And I could continue making modifications, and this is actually the best path. And whatever that best path is, so we take an infimum over all possible paths that connect X and Y, and that's called the passage time between any 2 points. And we call it the first passage time because I'm taking an infimum. So that's why it's called first passage percolation. So any questions on the model? I want to make sure the model's clear. Okay, so let's just have some fun. So I started with 20 units away. So I'm going to fix the origin and then move 20 to say 30. And then let's go 40. How about 50? And then I'll stop coloring everything because the graph will get a little busy, but here's 100. Here's 200. Now, here's something interesting. Look at, this was the intermediate point that we just saw. So from 0 to 100, it looks like this. But then when I go to 200, it seems that the best path completely bypasses 100. So this is a very non-local problem. Just because I use some geodesic from 0 to 100 doesn't mean that's going to be any resemblance from the geodesic from 0 to 200. So there's quite a difficulty in studying these interesting objects. Okay, and then let's go 500. And just to start seeing the fractal-like structure, here's 1,000. So you could ask a lot of interesting questions about this model. It's a very rich field with a lot of big open problems. But here was just one of them that captured my attention. So suppose that I look at the edges that you observe along a particular geodesic. So you go back to the previous page. This has some, ultimately, somewhere between 1,000 and 1,500 edges on it that it used. And for each one, I could just write down what was the edge weight that used. So, sometimes I have to use large edges, but most of the time I'm going to try to use green edges, those small ones. And so if I just store in what I call the empirical measure, So here's the Dirac delta mass. This is just a point mass at particular edge weight xe. And then I'm just normalizing so that it's a valid probability measure. That's just encoding which edge weights I used along the geodesic. Okay. Any questions about that object?
So when you say pi geodesic, an optimal path?
It is an optimal path. Yeah, so depending on the edge weights, there may be more than one optimal path. I don't at all assume uniqueness, but let's just say this is a geodesic. This is one of them, and you can pick your favorite one. So I'm just recording which edges I used, which edge weights I used. And then the question, which was kind of folklore, but was officially recorded back in 2015, is do these measures converge weakly? So in the weak topology on probability measures as n goes to infinity. And if that's the case, what it would tell us is that somehow there's an optimal strategy in the long run to get from 0 to some point very far away. There's some unique balance of low edge weights, high edge weights, medium edge weights that gives you the right recipe for getting a geodesic. So does this converge weakly? Really what we're interested in is the uniqueness of that possible optimal strategy. Okay? And prior to the theorem that I'm going to show you on the next stage, there was no positive examples of this. We had no examples of where there was a positive answer to this question, which is what we generally suspect. Okay, so now I'm going to use those same, yes, let's start at 30. Oh, this was the first graph when I used 20 units away from the origin. It used 30 edges in total, and here's a histogram of the edge weights. Now remember I told you they were uniform on 0, 1, so the biggest edge weight you could use is 1, the smallest you could use is 0, but of course I have some tendency to use small edge weights because I'm looking at a minimum rather than a maximum. And then we're going to go through that same sequence. So here was 30, here was 40, and you can see it's starting to clump closer to the origin. Here's 50, 100, 200, we have a little bit of spike, that's interesting. 500, now see it's not quite settling down into something we think should be monotone. You see it a little better at 1,000, but it does take a while to actually see any consistent pattern. And the question is, already this takes a while to simulate. The question is, if I send n to infinity, do I get a limiting histogram, some limit shape to this graph? So here's the result that I was able to attain, is that let's assume that maybe you're not using uniform edge weights, but you're using some function of uniform edge weights. So this tau is just some map that pushes those uniform edge weights to be a different distribution. And there actually is no loss of generality in this because any random variable distribution can be obtained in this way. You can observe it as a function of uniform random variables. If you observe the uniform random variables and then their function as the edge weights xe, then the statement of the theorem is that for a dense set of choices of tau, say with respect to the uniform norm on measures or on functions, then indeed the empirical measures that I defined on the previous page converge as n goes to infinity with probability 1. So with certainty, we do have all those histograms converging to a nice shape. Now, this is quite an interesting result because we get a dense set of choices. So here are just some examples. You can take functions that are piecewise constant, where the heights of the constant things are almost any choice if you just sample randomly. Certain functions that are fully supported on the non-negative numbers. And you can even take differentiable functions, k times continuously differentiable functions. You can find a lot of examples, but I can't name a single one of them. So there's this conundrum in a lot of random growth models where we can prove pretty general results sometimes, but actually nailing down one specific example requires a different set of tools, and that's part of the discovery process as well. So any questions on this theorem statement? Yes? Say that again? G del, yes, yes. So what you will see on the previous page is exactly the reason why this theorem is true. And in fact, I'll tell you exactly where G delta would come in. Okay. All right, so now let me tell you how I proved that theorem. And here's where the law of large numbers comes in. So I've graphed here as a table all of the different n values we assumed. And then here is the passage time between 0 and n units in the horizontal direction. And then I divide by n just to put everything on the same scale. And you see here's the numbers. They actually look to be kind of decreasing. There's a reason why that's the case, namely because this process is subadditive. And if you apply the subadditive ergodic theorem, which was actually the original purpose of using this theory, was this model in particular. So it inspires quite a rich mathematical tradition. If you send n to infinity, then you get what we call the time constant. That's just the limiting value. This is a deterministic value kappa of this right-hand column. And so now the theorem that is really the backbone of what was on the previous slide is this one. So again, you're in the same setup. You have some function of the uniform random variables. And all that I do is I represent this constant kappa, whatever it may be, I don't know. But whatever it is, it's represented as this variational formula over a certain set of non-random measures on 0, 1. So I've represented this deterministic constant as a deterministic formula. Now, don't worry so much about what m is. It's a subset of measures on 0, 1 because these are random variables on 0, 1. But what's important is that as a function of mu, this little integral is just a linear functional on top. So I've just got an infimum of linear functionals, right? So this is also known as a support function. This is generically concave, just automatically, it's a two-liner. And what do we know about concave functions, or if you like thinking about convex functions? They are generically differentiable. And what it turns out is that the points of differentiability for this map, which sends whatever functional you chose for tau to the deterministic constant kappa, ends up being a concave function on some function space. And you can choose the function space to be whatever you'd like. If you choose a separable Banach space, then there's a G delta subset, a dense G delta subset on which this is differentiable. And you can choose a variety of different function spaces, and each one of them would correspond to one of these results. And so whenever this map is differentiable in whatever the appropriate functional sense is, that gives you an example where there's a limiting empirical measure. So we've connected this functional analytic question back to this physical question of limiting empirical measures. And again, I can't name any specific point of differentiability. I just know that they're dense. And I'll mention that this variational formula in particular was just designed to solve the problem that I was interested in. It was really tailor-made. There are other variational formulas for this same constant, but they attack the problem from a different perspective. So they're useful for different things. So there's not one right way of doing these problems. There's maybe a variational formula that's nicely made for your particular question. All right, so any inquiries about anything I've said here in chapter 1? The theory all goes through this kind of abstract stuff, but this constant will be a different thing. And potentially this map will be differentiable on a different set of functions. I don't think that would be the case, but yes. Other questions? Okay, fantastic. All right, so let's go to chapter 2. And now we're going to kind of repeat some of the structure, and we'll also introduce some new objects just to get some exposure to these things. So here we have the disordered motion sector. So this is our inspiration here in Newton, who gave us, of course, the laws of motion. Now let's talk first about the canonical motion. From a probabilist perspective, that's Brownian motion. So let's just play a video just to remind you what Brownian motion looks like. So here is really, well, it's simple random walk, but of course we have to discretize. So this is kind of what Brownian motion looks like. At every stage, so here you're moving forward in time, the walk is just choosing with probability 1/2 to go up or with probability 1/2 to go down. And it's making that independently at every step. So then you can see as I kind of change the scale, this fractal-like object emerges, and that limiting fractal object, if you make the appropriate scaling, that's Brownian motion. Okay. So that's our kind of base model. Right? Think of this as like Euclid's geometry. This is the nice symmetric, we can study the heck out of it. This is what we understand well. And what I'm going to do is now introduce a random field that this now random walk or this Brownian motion has to interact with. So now things get noisy. All right, so here I've given you kind of just the conceptualized picture. We have to describe the model, so I'll make some definitions precise. And you could do this in a variety of ways. You could do it in a continuous way, but ultimately to simulate, you got to do it discrete. Anyway, so let's just start with a discrete model. And the one that I'm going to describe is called directed polymers in random environments. It was originated in this physics paper back in '85. All right, so we start with the law of the simple random walk. So, this is the one-dimensional simple random walk with time on the bottom axis. Then again, you're just choosing to go up or down at each step with probability 1/2. That's the base model. And then what I'm going to do is at every point in space-time, I'm just going to lay down another random variable. So here I actually have, again, I was uniform random variables. The black ones are small, the white ones are large. And now I have to tell you, how does this random walk path interact with this random field, this disorder? Again, these are the disordered variables. They're IID random variables, again, in both time, that's I, and space, that's Z. So it's a dynamic random field as well. So here's how it interacts. So again, just like first passage percolation, we're just going to add up the weights that we see along a trajectory. So if you choose a particular trajectory, a vector, W, so you have to choose here's W0 at the origin, W1, W2, W3, W4. You add up all of the vertex weights, all of these disorder random variables that you see, and you multiply by this inverse temperature parameter beta, that's just some non-negative constant. And then you take the exponential, and this gives you now the density function of what we call the Gibbs measure with respect to this probability measure P, which was just the law of the simple random walk we started with. And this Zn beta, it looks pretty innocuous at first. It's just a normalizing constant, so that this Gibbs measure is actually a probability measure. So if you'd like, here's the definition of Zn beta. It's just the integral that it has to be in order for this Gibbs measure to be a probability measure. All right, questions about this definition? So this is our model. We say that the walk interacts with the potential in this way, and then this is our normalizing constant. And that normalizing constant will actually be the key to our law of large numbers in a bit. Okay. So now what I want to show you is a sample from this Gibbs measure. And I'm not going to show you one sample, I'm going to show you 100 samples. So I laid down the random variables, I construct the Gibbs measure, and then I'm going to sample from that Gibbs measure independently 100 times. And here n was 100. So the length of the polymer, I took 100 steps in your random walk. And here we're just seeing what the paths look like that you sample from the Gibbs measure. And this looks a lot different than what we were seeing before. Notice it kind of has this same trajectory. It almost looks like you're sampling the same thing every time. Now, it's not the case. These are independent samples. It's just that somehow the Gibbs measure has found the route that it tends to like to be around because the random variables are favorable there. Maybe all the x's are quite large. And what I've actually asked this path to do every time it crosses a vertex is lay down a little cookie crumb to tell you that I was there at a certain time. And now as we continually sample, you'll see a trail of cookie crumbs. And wherever it's darkest is where the most cookie crumbs were laid. Okay. So now we've got 100 trials, but now let's speed it up. And in fact, now you see that cookie crumb trail really emerging. Right. So this is somehow, quote, the favorite corridor that the polymer likes to be in. Now, the basis of this thing was simple random walk. I'm not lying about that, but it looks very localized. And so what I say in the coming slides, we'll try to quantify that in a bit. So here's the Gibbs measure. And just to make sure I'm telling you the truth, let me do the same simulation with actual simple random walk, and that would be it. So this, you see this nice diffusive behavior. Here it's kind of more densely packed because I had to start at the origin, but then it diffuses outward. And also notice that this actually gets further away from kind of this origin point than the actual random walk. So somehow there's a different scaling behavior that you observe, and quantifying that is a major open problem. Yes. So I wouldn't go so far as that. The actual objects that you get in the limit are a bit less certain. I can tell you that the distance from the origin at scale, if you run out to time n, should be of scale n to the 2/3. In simple random walk, it would be n to the 1/2. Right? That's the diffusive scaling. Now, if I change this to a higher dimension, all of a sudden we don't even know. So we know things pretty well in one dimension, but higher dimensions not so much. Other questions? Okay, so here, let's go back to this partition function I said. So remember, that was just the normalizing constant for the Gibbs measure. And even if you don't quite remember the formula, don't worry about it. Just know that this is the object that you want the law of large numbers from. Okay. You could do certain probabilistic operations. So if I took the expectation of it, you can apply Fubini's theorem, carry it through the integral. Now these are just random variables, and so this factorizes. You just get the same expectation raised to the nth power. And then I've just written it as this exponential moment. Okay, so here's the statement you need to know that is classical by now. Is that if you take the log of the partition function, you're taking log because we put an exponential in there. And then I do that same linear scaling. So now I'm going to divide by n because I've got n factors in here. And then I take limit as n goes to infinity, that converges to a new deterministic constant. Again, I'm going to call it kappa. And it depends critically on whatever inverse temperature beta you have. So you can imagine if beta is very large, then the random environment has a big effect. That is, it gets more localized. If beta is small, say beta is 0, then you just recover simple random walk. So this beta is a tuning parameter that tells you how close to simple random walk do you want to be. And indeed, okay, so this inequality, if you apply, so this equality, if you apply Jensen's to it and use this fact, then ultimately what you get is that this limiting constant is at most the exponential moment of this random variable. Okay, so don't worry so much about that. What is important is that this allows us to define a phase transition. So for small values of beta, so that is close to simple random walk, it kind of resembles simple random walk still. These two things are an equality. And what that says is that Jensen's inequality was really, in the limiting sense, an equality, so not much was different, that this random variable is really well concentrated. And then when I go beyond a critical value of beta, which depends on the disorder, which depends on the underlying dimension, we call this the low temperature regime, because remember, beta is the inverse temperature. Then this becomes an inequality. So now this is really, I mean, this kind of looks abstract. This is how the physicists would define the phase transition. But for all purposes, now just remember that this is the law of large numbers, and there is some phase transition, where I think beyond a critical value of beta, things should behave macroscopically differently. And now how are we going to get that? Well, we're going to study a variational formula. Okay, so now I'm going to prepare you for how we construct this variational formula. So remember, here's our definitions. This is the partition function. This is the Gibbs measure that it helped define. And now let's imagine that I change n to n plus 1. So then you recover this top line. And what I did was I just pulled out, if n is now n plus 1, there's an additional factor here. So I just pull that factor out. I've just removed that last term in the sum. And now notice that this exponential combined with the p at the end, that looks a lot like whatever the Gibbs measure was at time n. So I'm just going to write gn. And then what is remaining is this additional factor. And all that I need to do to account for the random walk step is look at the neighbors of where I've been most recently, because that's the only place you can go next. Wherever you are at time n, that's wn. And then you can only move to one of the neighbors of wn, of which there are 2d many. Okay? So this is just working through definitions. And this limiting object, or this object over here, we call the endpoint distribution, because it says, if you look at the polymer of length n, where do you end up? And this gives you the distribution of where you believe to end up. So in that original picture, you saw that you were likely to end up in that top right corner. And the endpoint distribution would be concentrated there. Now, if I take this Zn and I divide it over to the other side, then we get this abstract concept that this ratio of partition functions is some function, which depends on beta, because here's the beta, of the endpoint distribution. Right? The endpoint distribution is on the right, the ratio is on the left, it's just some function of it. Now, if I actually take logs and then rewrite this log as a telescoping sum, so all of these middle terms would just cancel out, you'd be left exactly with this, because zi, when I equals 0, z0 is 1, so log of 1 is 0. And if I rewrite these ratios in terms of these functions, then I get this kind of formula, where this is now the ith endpoint distribution. So remember the mu, that's that functional order parameter appearing. So this is the key physical object to pay attention to. And what does this look like? Well, this looks like a Cesaro average of some functional of an evolving stochastic object, namely these endpoint distributions. And so there's a hope, and in fact, it's actually a realized hope, because these Markov, this endpoint distribution chain is a Markov chain. So in fact, you can use ergodic theory, hopefully, to understand this Cesaro average as just converging to some stationary measure. And indeed, that's what ends up happening. And there's a lot of details that you have to work through that use actually tools from PDE theory, namely concentration compactness, to construct the right space on which you can perform this ergodic theory. But beside those details, what is important is that that limiting constant, that law of large numbers, I can write it as a variational formula now. And the functional order parameter that helped me do that is this measure on endpoint distributions. So now this, that the constraint set of the variational formula is a measure on endpoint distributions. So this is focused on the endpoint. And there are other variational formulas again, but they're not focused on the endpoint. So this was a new observation that you could write the variational formula in terms of some endpoint distribution. So now I'm going to show you a sample of that endpoint distribution. So on the bottom, you'll see simple random walk. And on the top, you're going to see the endpoint distribution as I change the length of the polymer. So on the bottom, you're going to see this nice bell curve that emerges, right? That's really the central limit theorem. And on the top, what you'll see is that there's just kind of these preferred sites. So this is representing the probability that at whatever particular time, the polymer likes to be at that location. So here, well, let me move to the next slide. What we see is that even at time 100, there's some preferred sites that the polymer likes to be at. So there are favorite endpoints. Those are that localized points in that corner. Whereas simple random walk, it's diffusive. And if you scale it right, you'll get that Gaussian curve in the limit. All right, so if we actually want to make a theorem out of this, and this is really a consequence of the variational formula, then here's the theorem. So if beta is greater than that critical value, so if we're in the low temperature regime, then that endpoint distribution that you see down here asymptotically concentrates on a stochastically bounded number of points. So if that doesn't mean much to you, just remember there's like 100 points, and with probability close to 1, the endpoint distribution is just going to be concentrated almost all of it on the 100 points. Now those locations of the 100 points will be random, but there's some just finite set of points that I can find that capture almost all of the mass of the endpoint distribution. Whereas for simple random walk, of course, I need order square root n many points to capture all of the endpoint mass. So what's critical is that this bounded number of points doesn't depend on n. And moreover, we were able to show that these points are close together in some geometric sense, right? That there's kind of a single cluster. There's not one cluster over here and some cluster over there. We're able to show that that happens a positive fraction of the time. Okay. We'd really like to say it happens all the time, but there's a technical challenge in that. And just to complete the theory, if you're in the high temperature regime, so that is you're looking more like simple random walk, then like simple random walk, the largest atom, so the size of, say, this peak, would actually tend to 0. So there are no favorite sites in the high temperature regime. So there really is this stark phase transition between the two models. And this consequence is called asymptotic pure atomicity, because in kind of theory, this is now a purely atomic measure in the limit, whereas this would be a continuous measure that would be a Gaussian distribution in the whole limit. And this is a bit surprising because the best previous result for this low temperature case had only studied the largest atom. So by using the variational formula, we're actually able to bootstrap that largest atom all the way up to the entire endpoint distribution. And a similar strategy has since been carried out in several other settings. So it's been nice that this general method has been seen extra utility in new models. And if you're curious about not just the endpoint localization, but localization of the entire path, that is finding the corridor of those cookie crumbs, there are also results in more restrictive settings of those types. So here's a sequence of papers. So that is kind of the ongoing work. We'd really like to say that the path is completely localized. And we can say that to some degree, but there's certainly gaps to fill. All right, questions about anything I've said here? Okay, so this has been chapter 2. We've seen some emerging theorems or emerging themes. Please, Zach. Not at all. So every theorem I put there was actually general. Those were general dimensions, yes. So the beta critical will depend on the dimension. And actually in dimension 1 and 2, beta C is 0. So as soon as you have any disorder, actually this phenomenon occurs. But in dimensions 3 and higher, you actually need a positive beta. Other questions? Okay, so now let's go to our last subject. This one's pretty fun. So here, of course, is James Clerk Maxwell, who gave us Maxwell's equations, which describe electromagnetism. And within those equations, there still are a wide variety of physical phenomena that are difficult to understand. And I'm going to describe one mathematical approach to that. So let's start with something that's non-disordered. So this is not a disordered system. This is the Ising model. And if you haven't seen it before, it's a model for ferromagnetism. So that is spins. So each site here is going to get either a plus spin or a minus spin. So it's either up or down. And what the ferromagnetism model says is that more likely than not, the spins like to be aligned. So the spin here likes to agree with the spin here. And this is captured in some Gibbs measure by taking this inner product. So sigma I and sigma j like to be either both +1 or both -1, so their product gives you a positive rather than a negative. So that's the easing model. And again, there's this inverse temperature parameter that tells you how much you care about that inner product. And now if we add disorder, so here, let me also say, if you kind of imagine this as a three-dimensional picture, so this is a two-dimensional slice of a three-dimensional object, the magnetic moments now are vectors. And then what ferromagnetism says is that all the vectors should be aligned. So this is what it looks like in your standard fridge magnet. All of the magnetic moments are aligned. If I add disorder, so that is I put a random variable xij, so say it's like a normal random variable that can be both positive and negative, then sometimes sigma I and sigma j will like to be aligned, and sometimes they won't, depending on the sign of xij, and also the magnitude. So this disorder is attached to now the links that connect these different constituent particles. And so there's a phenomenon called frustration where now the magnetic spins aren't really sure what to do. So such models actually capture magnetic dilute alloys. So for instance, if you combine copper and manganese, you get a model that is well approximated, at least in theory, by such a disordered system. Okay. Now this is a very hard model to study that we know basically nothing about. So along with the physicists, we've retracted ourselves to another model where I've replaced the lattice with just a complete graph. So in this way, I've replaced the underlying geometry to just the complete graph where there is no geometry. Every site interacts with every other site. So now that sum that was just over all pairs is now over all pairs with no restriction. So now there's no link. It's just all the time there's a link between every two sites. So here compare, this is when I was a neighbor of J, and then when I go here, it's just all pairs ij. So this is now called the SK model for Sherrington-Kirkpatrick. And this now is giving us some version of a mathematical model we can hope to solve, but the math is actually still rather difficult. So let me give you the story of this SK model. So again, there's a normalizing constant. This is just the thing that makes, when I take this expectation of this exponential over all elements of the hypercube, I get a valid probability measure. Again, that's going to be the law of large numbers object. And here let me introduce a different kind of limit. So instead of sending n to infinity, you could send beta to infinity. And what this gives you is what we call the ground state energy. So if I take this limit, I put a minus just so we can take a minimum here. So it kind of resembles that ground state. We like to think of things at the bottom. Then you would just be minimizing this complicated functional on configurations. So viewed as a function of the configurations where you have to choose at every site of either a +1 or a -1, if I minimize, that's called the ground state energy. And once I do that, this is for whatever reason is called the dean's problem. And here's the story we tell. If all of these sites actually represent students, and they're either in the +1 dorm or then the -1 dorm, then the dean has to figure out how do I arrange those students depending on some random interactions. Some students like each other, some students don't. And then you have to minimize over all of this so you get kind of the best possible scenario. And there's not going to be a perfect match, but in general, you want to kind of appease everyone or maybe displease everyone as minimally as possible. Okay. Now, I actually talked to a dean today. This is not actually what they do. Okay. I don't know who gave them this, who gave this problem the name, but apparently they didn't think much of deans. Okay, so this graph, which tells you this energy, this configuration of ±1 spins, and then you want to minimize over all choices of that, depending on the disorder, we call that the energy landscape. And if you're hoping to minimize this function, what would a great energy landscape look like? Well, just conceptually, it would look like this. I wonder where the minimum is, right? Well, it's going to be right here. And moreover, there's only one local minimum. So if you did any like gradient descent algorithm, it's always going to converge to the same thing. Now that's a good landscape. Here's another good landscape for a different reason. This one's completely flat. So now every point is a local minimum. And so intuitively, what it means is that you can just sample any point and sample any other point. They have nothing to do with each other, but they're both local minimum. Okay? The landscape is still pretty easy to understand. Now, this is not what the spin glass landscape looks like. Neither of these cases are. It looks a bit more like this. And so what this landscape is trying to capture is there are valleys within valleys within valleys. There's an exponential in n number of local minima. That's a provable fact about this landscape. So it's very hard to understand. But even so, this idea of focusing on the landscape proved useful for at least one person, namely Giorgio Parisi, who actually won the Nobel Prize in a large part due to what I'm about to describe on this slide. So what he said is, let me sample two independent configurations, again, from the Gibbs measure, not just uniformly at random, from the Gibbs measure. And I'm going to measure the overlap, so the similarity of those two configurations. So this is now some statistic that should be a big N. But this is some statistic that if they're -1, that means they're very anti-parallel. If it's +1, they're very parallel. And if they're close to 0, they're roughly orthogonal. So this is just an inner product that's scaled by n. And then what Giorgio Parisi said is that let's assume that these two are independent samples from the Gibbs measure. And we're going to say that there's some limiting overlap measure. So this is now a random variable. And let's just assume that random variable has a fixed distribution. And then given that distribution, what is a remarkable fact is that you can actually compute what the free energy quote should be. So you assume this kind of backwards thing where I know what the overlap distribution is, and then I can compute under that assumption the limiting free energy. And it took us over 20 years to figure out that, in fact, this is the right thing to do because you can optimize over all choices of mu now. So you say fix mu, figure out what the free energy is, and then optimize over that assumption. And in a series of mathematical works, this was actually made rigorous. So these Parisi works were of non-rigorous techniques. And then we have a long history of math that has not only proved this formula in rigorous sense, but it generalized it. So this is now called Parisi's formula and is the centerpiece of spin glass theory. And in particular, it introduces for us a natural phase transition. So again, there's a high temperature regime, which is when the minimizing measure to this variational formula. So this is just some variational formula over measures. When the minimizing measure is just a Dirac delta function, namely at 0, so things are orthogonal, then we call this the replica symmetric phase. Okay, so just think, this is kind of like, it doesn't really look like much different than just sampling the hypercube uniformly at random. Okay. And if I go make beta sufficiently large, so this is the low temperature regime, then eventually the minimizing measure is supported on more than one point. And this is called replica symmetry breaking, or RSB. And a major open problem, perhaps the biggest open problem in this field, is to understand that minimizing measure in the RSB case. Namely, how many points are in its support? Is it 2, 3, infinitely many? We'd really like to understand that. So there are bases for conjectures, but at present, the progress is rather minimal. So this is the kind of classical story. Now, the more modern version that has evolved in the last few years is the question of what if I made the disorder depend on the two things it was linking? Because everything before was all still symmetric. I had the complete graph, but the disorder didn't depend in distribution on what the two things it was linking. So we have what we now call multi-species models, which I partition that configuration space or the set of students into several species. And then I assume, so here are, for instance, we go back to that Dean's problem. Now I have the freshmen, the sophomore, and the juniors and the seniors. And let's just assume for consistency that the proportion in each species now converges to some constant. And then what we're going to do is allow the distribution of this disorder to depend. It's still a normal random variable, but it will depend on which species are the two individuals. So now maybe the freshmen care a lot about which freshmen they're associated with, but they don't really care much for which juniors they're paired with. So this now captures some kind of slightly less mean field model that's a bit more realistic and also can help us study real world networks. And in 2015, Panchenko proved a Parisi formula for this model. So this generalizes what Parisi did to this multi-species setting. And that in turn allowed us in a paper of 2019 to prove that symmetry breaking does occur beyond some explicit curve, which isn't worth putting on the slide, in phase space. So this just said there is a low temperature regime. Already that was quite striking because this variational formula that Panchenko proved was rather complicated. So we said there is an actual phase transition. This was later improved. We were very happy to see this work of Day and Wu. And to say a bit more, let's take one step back from reality. I'm going to replace all of the hypercubes with spheres. So now it doesn't really represent individual students, all of those students are clumped together in one single vector on a sphere of the same radius. But this is now called the spherical spin glass. This actually goes back to physicists who played this trick a long time ago. And for this model, when I actually relax now from hypercubes to spheres, we can prove something really interesting. That if symmetry is broken for some species K, so if some species is exhibiting low temperature behavior, and there's some interaction with some other species L, then symmetry is also broken for that other species. So this says that there's one phase transition for the entire model. It's not like species 1, species 2, they all interact, they all have a phase transition at different times. They have to have a phase transition simultaneously. And this was a very surprising result. We really did not expect the mildness of this condition. And there was no basis in the physics literature for any predictions. And moreover, we can establish there's a bijection between the supports of the minimizing measure. So there's a minimizing measure for species K and a minimizing measure for species L. And those two measures have the same bijective support. And here, I'll put on this last slide that all that's important is that there's a variational formula. Again, these are inspired by Parisi. And there's actually another formula that's inspired by two physicists, Crisanti and Summers. And here, we've had an additional factor of there's identities that allow you to prove that these two variational formulas are actually the same. And it was not actually these individual formulas, but the identities needed to show that they're the same that allowed us to prove the result on the previous page. So what you've actually observed is 3 different kinds of methods. So in the FPP, we established the variational formula to attack a specific question. In the polymers, we got a variational formula and then figured out what question we could attack it with. And then here, we actually knew what the variational formulas should be ahead of time, just by kind of using physics predictions. And it was the identities that gave us those variational formulas. That method along the way was the thing that allowed us to prove these things. So the variational formulas are not just useful in one way. You have to be flexible in how you use them to attack the problem of interest. So this is, I hope, a nice introduction for you for disordered systems, an invitation to talk more. Thank you very much for your attention. And here are all the references you can do. Thank you.
Have you looked at all, maybe more for the first 2 parts of your talk?
Sure.
Have you looked at sort of analogous questions for graphs that aren't very closely integer lattices?
Sure.
Things like trees.
Yes. Yes. So for trees, it's actually considered to be a simpler problem. And the kind of universality class that these models belong to will behave differently. So one interesting thing on the tree is, for instance, take that passage time or that partition function, whatever the law of large numbers object was. On a tree, that object in the probabilistic sense has fluctuations of order 1. And so what this actually means is that the localization that occurs will ultimately have that kind of concentration on a few points only occasionally. And so on the tree, it actually behaves quite differently. And it's exactly this kind of difference between the fluctuations of that law of large numbers object in the tree versus the lattice that we haven't yet bridged. That if we were able to bridge that and study the fluctuations again back on the lattice, we might be able to say more. So the answer to your question is yes, this is very interesting. Often the trees give us a first order model that, like the breakdown from the Ising model to the Edwards-Anderson, and then we moved to the sharing to Kirkpatrick. So I replaced the lattice with a complete graph. That's like replacing the lattice also with the tree in the other 2 models. Please, Zach. Yeah.
Is there any reason to think that, or are there any examples where there's sort of different phase transitions for different populations when you relax the sort of multi-species problem?
Sure. So yeah, the striking thing is that relaxing for us means that the 2 species can't interact at all. So certainly if I just have the 2 species not interacting, then what that means is that it's kind of like the product space of 2 independent models. And so you could kind of tune one to make a phase transition at a different point than the other. So yeah, so what was surprising was just how weak those conditions were. Now, whether or not this translates back from the spherical models to the easing models on the hypercube, which is kind of the more physically relevant model, that's an open problem. Thanks very much.